A quick recap: the course is 5 units. We've done the first 3 already, and we'll be beginning Unit 4 today with bridging the technical commercial gap. This is a hands-on unit, so we'll have 6 labs. In each lab, we'll be focusing on one stage of data science life cycle. The first lab will begin with understanding the business problem. We'll look at some example data sets and business problems and use a structured approach to selecting one or two. In the second lab, we'll explore this data. We'll be developing the solution and modeling in the third, followed by evaluation of the developed models in the fourth lab. And in the fifth and the sixth, we'll be looking at validating or approaches and techniques to validate this with the business and operationalizing the outcomes. All of this work will be conducted using Python and Jupyter notebooks. Let's begin with 4.1, Understanding the Business Problem. We begin with a list of candidate datasets. The first one being retail sales forecasting. The source of this dataset is Kaggle. The size stands at about 3,000 plus stores and daily sales data for multiple years. It's daily sales data with store information and promotional activities, and we could use this for time series forecasting, linking models to business strategies. Another candidate is the bike sharing demand dataset, the source being Kaggle again. Size was around 17,000 plus data records with 12 features or attributes, columns, so to speak. This contains hourly bike rental data with features such as weather, time of the day, holiday information, and so on. And it's excellent for regression modeling, so we can actually predict bike rental demand by season and by time of the day or day of the week, etc. And this can help us explore urban mobility solutions and potential alternatives. And the third data set is the adult income, source being UCI Open Data. Contains approximately 32,000 records and has 14 features. We've got demographic information on individuals, including age, education, occupation, income status, and so on. And we could use this for classification, where models to predict whether an individual earns above or below $50,000 can provide us socioeconomic insights influencing income levels. The penultimate candidate in our list is the World Happiness Report. And this is over a number of years, contains data for over 150 countries. There's several features or factors contributing to happiness rankings, including gross domestic product of the country, social support offered by the state, life expectancy of the individuals that relate to healthcare provision, and then freedom to make life choices, and so on and so forth. This could allow us to do some multi-factor analysis, visualization of happiness scores across countries. We could also model relationships between socioeconomic factors and happiness, and we could build a narrative around the implications for policy and societal well-being. And finally, California house prices, which contains around 20,000 rows, and it's got housing prices and various features in California, including location, size, and different amenities. And we could use this one for regression modeling, much like the bike rental demand data set. We could explore and visualize the data, build predictive models, regression models, and create a story line or narrative around housing market trends in California. So out of the two regression data sets, the bike sharing one and California housing prices, we'll take the first one because bike sharing is a data set that hasn't been used as often as the housing prices data set in machine learning literature. When it comes to retail sales, because it's time series and this is an introductory broad course, we want to do either classification or regression rather than time series forecasting. That can be left for another course and another time where we focus deeply on machine learning. And finally, World Happiness Report is multi-factor analysis, and therefore we drop this in favor of classification or regression. That only leaves the adult income dataset, which is the only one we have for classification. So Let's compare bike sharing demand and adult income data set against each other to select which one we would like to use. We compare the two against each other using a number of features: what source, what size, what type of problem, target variable, key features, data complexity, exploratory analysis, real world relevance, modeling techniques, performance metrics, narrative, and engagement level. In this case, we see that UCI Open Data is the source for adult income dataset and Kaggle is the source for bike sharing. The size is a clear indicator. So in this case, the size for the adult income dataset is 32,000, whereas 17,000 for bike sharing. The type of problem, as we've already highlighted, is classification, or in other words, binary classification. It's a 0-1 problem. It's either one class or the other. And with bike sharing, it's a regression problem because we're going to be predicting the rental count of any particular day or hour. In terms of target variable is income level for adult income because we're predicting whether an individual is earning less than or equal to $50,000 per year or greater than that. In bike sharing, the number of bike rentals is the target variable. We have a number of features. With data complexity, we have quite rich demographic features with categorical variables. In bike sharing, we have time series data with temporal features, so they're quite different, equally interesting. Exploratory analysis will have to look at relationships between socioeconomic factors relating to adult income. In this case, it's seasonal trends and weather impacts and usage patterns. Real world relevance, it can apply to socioeconomic discussions around inequality, policy impact. With bike sharing, it's urban mobility, sustainability, transportation, etc. In terms of modeling techniques, we do logistic regression, which is a classification technique, decision trees, or even SVM based classification, which is support vector machines, or neural network based classification. For bike sharing, we would have regression, which is truly regression, so linear regression, random forest, XGBoost, and so on and so forth. In terms of performance metrics, we would use accuracy, precision, recall, area under the curve for classification of adult income. And with bike sharing, we'd be using regression based metrics like root mean square error, R squared, mean absolute error, etc. In terms of building a narrative, the first one allows us to have insights into economic mobility and inequality, and the second one allows us to work on urban planning and transportation improvements. And let's do both of these because then we'll have at least one data set for classification and another one for regression. And so we begin Unit 4 and 4.1 with understanding the business problem. We will develop a solution from end to end. We will start looking at what the data provides us with, what the business problem is. It's essentially bike sharing demand in urban environments. We look at it using the approach of 5 Ws and a H: the what, the why, the how, the who, the where, and the when. What is it? Well, we want to predict the number of bike rentals in a city based on various factors such as weather, time of day, seasonal trends, usage trends. Why? Because it'll allow us to understand rental patterns and help improve bike sharing services, improve and inform city planning, and promote sustainability in transportation. How? We will build a predictive model using machine learning to forecast or predict bike rentals per hour or per day. Who is it for? Well, it could be used by city planners, bike sharing companies, and urban mobility researchers. Where is it situated? The data set has data on a bike sharing program in a metropolitan area, and when the data spans multiple years, providing seasonal and temporal insights over at least a couple of years. Donated in 2013, again on UCI ML repository, contains hourly and daily count of rental bikes between the years 2011-2012 in capital bike share system with the corresponding weather and seasonal information. Multivariate, integer, and real values can be used for regression, contains over 17,000 records or data instances, and has 13 features or attributes, including the instance or the record index, the DTE time of the day and date, that's date rather, month, hour is going to give us time of the day, year and month, season, holiday, weekday, and so on and so forth, as well as weather. As we can see, quite a number of publications have already used this data set. Again, you could download it or you could import in Python with um, package installation, UCIML repo using pip install, and then fetching the data directly in your script. We load up a Jupyter notebook. This is based off of Anaconda Continuum Anaconda distribution. In the first instance, we import pandas, which is the data frame uh, processing library, and we give it an alias, import pandas as PD. Import numpy as np. Numpy is the number Python library, which allows us to use a lot of mathematical formulas on arrays. We import matplotlib.pyplot as plt, again giving it short aliases so that it allows us quick reference and calling. And import cbon as sns, again a visualization library that we've looked at in previous lectures. We load the dataset by using pd pandas.read_csv function. The read.csv function takes a path name and a file name, which is going to load the dataset into this variable data. We preview the data by calling the head function on data, which gives us the first 5 rows in data which has been loaded. So we run this and we run that as well, and we see that it has a first column, as we saw, instant, which is the record index, the date of the day, 2011, season 1, year 0, month, the first month, holiday, there's no holiday, weekday, it's the 6th, the 0th, the 1st, the 2nd, and 3rd, working day, whether it's a working day or not. These 2 days appear to be Saturday and Sunday. Weather situation, which is some code that we can look up by going back to the UCI webpage for this dataset. So A temperature is normalized feeling temperature as opposed to temperature, which is normalized temperature, feels like. And casual is the count of casual users, registered is the count of registered users, and CNT is the count of total rental bikes, including both casual and registered. Temperature and A temperature, which is the normalized feeling temperature, humidity, wind speed, casual, uh, the riders who aren't registered and they're casual renters of bikes as opposed to registered users of bikes, and the count, which is total number of the total number of users renting the bikes on that day. So we can look at a bit more information about the data. The data frame gives information in terms of its type, which tells us that it's a class pandas.core.frame.dataframe, a range index of 731 entries from 0 to 730 being the index. The data columns, there are 16 data columns in here. There are no missing values. As we see, all of these columns have the same number of entries. All of these are non-null, and the data type has been picked up automatically by pandas. So the date is not integer or float or anything else. So it's stored as an object. We could change this to date time depending on if we want to use it like that. Most of the other values or columns are in integer 64, and then there's a few in float type as well. The describe function gives us basic statistics of the data frame. So per column, we can see that each column has a count, mean, standard deviation, minimum 25%, or the 25th percentile, the 50th percentile, the 75th percentile, and the maximum value. So we can start to appreciate, for instance, if we look at humidity, then it's ranging from a minimum of 0.0000 humidity to 0.97 very high humidity, 50th percentile at 0.62, the standard deviation being 0.14, around a mean of 0.62. We already know that the data has no missing values, but we could use the data.isNull or dataframe.isNull function to see if there are any nulls in any of the columns. Now this is a bit tedious because we can't check each and every record to see whether there's a true here. So the easier way is to just call the sum function on that output, and it gives you a sum of each column for the trues, because false is represented by 0. If there are any true values in there, that would be 1, and the sum would pick those up and then give you a sum of all the ones. In this case, we can see that we don't have any null values. Looking at the data's frame's shape, it's telling us that it's 731 rows with 16 columns. We've confirmed that up above already. And finally, looking at unique values in each of the columns for data, we call the nUnique function, which is giving us the number of unique instances in the first one. Because this is an index of the record, of course, all of these will be unique. Because each day is represented by one record, therefore DTE day is also going to be 731 dates. The season has 4 different types of values, so 4 seasons. There are 2 years, so we know that 2011 and 2012, if we recall well. The 12 months, of course, there are 2 holidays covered here, 7 weekdays, clearly. Working day, 2. Weather situation, there are 3 different values. Temperature has 499 different values because it's a float value as well. A temperature is 690, humidity is 595, and so on and so forth. We'll start with exploratory data analysis in the next lecture.